Hey everybody, today we are talking about Unit 4 Lesson 3, and that's conditional probability, tree diagrams, and maybe some independence toward the end. So essential questions for today is how can I determine the order of conditional probabilities, and how can I use tree diagrams to find intersection probabilities and more? Let's start off with an example. We want to know what is the relationship between educational achievement and home ownership. We have a random sample of 500 people who participated in the 2000 census. We want to let HSG represent those that were high school graduates and HO represent homeowners. So in this two-way table, we can see that we've got the high school graduates and non-graduates, homeowners and non-homeowners. And we want to know what is the probability that a person is a graduate and owns a home. And we know that word and is referencing the intersection, right? So this is really talking about the probability that somebody is both a high school graduate and a homeowner. And we remember that from previous lectures. That says, look at the intersection between those two particular events, and that's our 221. And then we divide that by our total, 221 out of 500. So there's nothing really new there. But now the question changes. What is the probability that a person is a graduate given that they own a home? So now notice how the language has changed. We are looking at given that they own a home. We have a condition here. And the condition is that we are only considering those that own a home. Well, in this setting, how many of our 500 sample were actual homeowners? And that was 340. So 340, that's our total. That's our denominator. Now, of those homeowners, we want to know how many of them were graduates. Well, of those homeowners, it's not the 119, it's the 221. So it's the same numerator that we had before. We're looking at that same intersection cell. That just happened by chance. But what we're looking at now is a new denominator. And this is going to be the probability that somebody is a high school graduate given that they own a home. So the notation we're going to use is that vertical bar to indicate the given. Okay? Next question. What's the probability that a person owns a home given they are a graduate? So now the given condition has now changed. It seems like it's the same problem, but the order in which that is happening has changed. So now we are only considering high school graduates. And there are 310 total high school graduates. So that becomes our denominator, 310. We still want to know those that are homeowners among those high school graduates. So it's still at 221. So just by chance, it happens to be that same numerator here that we are looking at 221 out of 310. And this is representing the probability that somebody is a homeowner given they are a high school graduate. So you start to recognize the order with conditional probability like this. The given probability is very important. We also notice some different notation. And we notice how it's very closely related to intersection probability, but it's still slightly different. Well, let's investigate how. Conditional probability is this. It's P of A given B. That's what this vertical bar is representing. The vertical bar there is telling you given. And we calculate that using the formula by the probability of A and B divided by the probability of B. To me, the easiest way to remember that is it's the probability of both divided by the probability of given. Okay? Then we read that as P of A given B. If B happens, what's the probability that A happens? Now, if you're using a two-way table, a column or row total is going to be your denominator instead of that table total like we saw with intersection or union events from the previous lecture. Now, let's look at another example. Shannon hits the snooze bar on her alarm clock on 60% of her school days. If she doesn't hit the snooze, then there is a 0.90 probability that she makes it to class on time. However, if she does hit the snooze, there's only a 0.7 probability that she makes it to class on time. So there's a couple of things that we need to kind of unpack here and really look at when we're marking our text. Okay, and we first want to notice this if statement, right? If-then statements are huge indicators that we are looking at conditional probability. Also, you'll notice that we are looking at seemingly the same scenario, that she's on time. But what do we notice? It depends on whether she hit the alarm clock or not. So we say this is a conditional scenario because Shannon's on-time probability depends on whether she hit the alarm clock or not. We are given the conditional probabilities here. So a two-way table won't work because a two-way table is always giving us the intersection probabilities, not the conditional probabilities. So we need some other way to model successive events in order to answer this question. On any randomly chosen day, what is the probability that Shannon is on time for class? We turn to tree diagrams to answer this question. So tree diagram can model successive events. Consider event A happens. We have A happening or it doesn't happen. So we have P of A or P of A complement. A happens or doesn't happen. Then B happens. That sets off a huge chain of events that may or may not happen. The tree diagram is going to display that full chain of events given that A happens first. And what you notice with these tree diagrams is the conditional probabilities are provided for you at the end of these branches. This is an advantage of tree diagrams over the two-way tables. And we'll see what we mean as we start to look at this scenario with Shannon. So the first thing that we want to recognize when we read this problem again is, again, what's the first thing that happens? And it's going to be her decision to hit the snooze bar or not. So Shannon hits the snooze bar on her alarm clock on 60% of her school days. So we know that she's going to either hit the snooze, and that's going to be a 60% chance. What happens if what happens else? What's the other possible outcome? She doesn't hit the snooze. And if there's a 60% chance that she hits the snooze, that must mean there's a 40% chance that she does hit the snooze just by using the complement rule. Well, now, after she hits the snooze button, what happens? She's going to go to class, and it's going to be either on time or not on time. Whether she hits the snooze button or not, she's still going to class. She's still going to be on time or not on time. Okay, let's read through the prompt and see how we can fill out the rest of this tree diagram. You want to think about following the path. If she doesn't hit the snooze bar, it means we are following this path. There is a 0.9 probability that she makes it to class on time. So that's following this path. And what does that give us? 0.9. Okay, that's the 90% chance if she doesn't hit the snooze button. Now, what happens if she's not on time then? What's the likelihood that she's not on time? Well, notice that this is one of those basic rules of probability that these should always sum up to 1, and these should always also sum up to 1. So if we know that 90% of the time she's on time, what must be the probability she's not on time in this branch? That's 10%, 0.10. Now, look at the other branch. We are told that if she does hit the snooze bar, then she only has a 70% probability of making it to class on time. So that's following this path. That's a 70% chance. If there's 70% chance down that branch that she's on time, that means there's only a 30% chance that she is not on time. Now, what we have to do next in order to answer this question is to consider what are all the ways that Shannon makes it to class on time. And those are, well, she hits the snooze and she's on time, as well as she does not hit the snooze and she is on time. Those are all of the different ways that that can happen. So what we are really looking at is if we call on time being OT, that event OT, what's the probability she's on time? Well, it's the combination of these events, probability of hitting the snooze and being on time, as well as the possibility that she did not hit the snooze and she is on time. So we want to follow these branches. Well, how are we supposed to calculate the AND probability, the intersection probability? Well, we do some rearrangement. We rearrange conditional probability, we do so like this. We start off with this formula. Probability of B given A, notice that I changed some things around here and it doesn't really matter. It still follows the same process. Probability of B given A is the probability of both B and A happening divided by the probability of the given, that A happened. Well, here's what I want. I want to get this guy all by itself. I want to get P of B and A, the intersection probabilities by themselves. How do I do that? I notice that P of A is in the denominator. It's divided. How do I undo division? We do that with multiplication. Okay, what happens if I multiply P of A on both sides? Well, I notice that on the right-hand side, I've got a P of A in the numerator, P of A in the denominator. Those are going to cancel out. Then I'm left with P of B and A is equal to P of A times P of B given A. And that might seem really confusing right now. But what you want to recognize is, well, this is the first branch. And then this is the second branch. And all we are doing is multiplying down the branches, and you'll see how that works. So now you notice, same scenario, I've just replaced the notation with the words. And let's follow the branches to find first P of S and OT. Well, 60% chance here, 70% chance here. The rule says to multiply down those branches. 0.6 times 0.7 is going to give me 0.42. That's the probability of S and OT, that she hit the snooze and she's on time. Now we follow this branch. She does not hit the snooze, but she still somehow is on time. That's 0.4 times 0.9, and that gives us 0.36. Now, summing those two together, we end up with 0.78. And what does this tell me? There is a 78% chance, regardless of whether she hits the snooze or not, because we accounted for both of those outcomes, that Shannon is going to be on time. Now, that's using the formula and the rearranging, and that can be a little bit confusing. To me, I've always understood it in an intuitive way, and I always want to never take away your intuition. Here's what I read this as. Well, on 70% of 60% of all occasions, looking at this backwards, Shannon will be on time, right? 60% of those occasions, she's going to hit the snooze button. But on 70% of those 60%, she's on time. Now, that word of is really, really important. 70% of 60% of all occasions. Why is that word important? Of is the mathematics word for multiplication. And that tells me to multiply down those branches. So I look at all of the different ways in which she can be on time. Well, on 70% of 60% of the occasions, she's going to be on time, as well as following this branch, she's on time. On 90% of 40% of all occasions, Shannon will also be on time. Same idea, just a little different thought process to get me there to this same process of multiplying down the appropriate branches and adding them together. And that's how we work with a tree diagram. One way or the other, we see that Shannon is on time on any randomly selected day 78% of the time. Now, for probably the most interesting question and the true AP stats level question, we want to look at what is the probability that she hit the snooze given she was on time to class? So you start to think, doesn't that sound like it's the same exact question? And the answer is no, this is not the same question. This is not given to us in our tree diagram, because what we want to know is what's the probability she hit the snooze given she was on time. So Shannon gets to class, she's on time, and I say, I wonder if Shannon hit the snooze button or not. Let's try to find out. So what do we need to do for this? Let's go ahead and try to use that formula. Try to remember, because using the formula sometimes can allow you to do the more advanced stuff. This is not an intuitive question. So I say, well, I know that the conditional probability is probably both divided by the probability of the given. In this case, the given is that she is on time, and that's P of OT. So that's going to go in the denominator. And I know it's the probability of both S and OT divided by OT. If I'm savvy enough, I can start to remember, like, I already calculated some of these. Let's go and take a look at what did we actually calculate already. Well, I know that probability of S and OT, we did that by just multiplying down the different branches. 60 times 70% gave me 42%. Okay? Now, what about P of OT? Well, that was the ultimate question that we had in the last prompt. That was summing together all of the different ways that she was on time, and that was 78%. So now all we have to do is realize this is my numerator, this is my denominator. Go ahead and plug them in to our formula. 0.42 divided by 0.78, and that's going to tell me that Shannon hit the snooze button given she was on time on 53.85% of any occasion. And that's how we can really start to wrap our heads around complex probability utilizing tree diagrams and just a couple of very simple formulas and start to ask really, really interesting questions. All right, that's it for this lesson today, you guys. Thanks for watching. Have a good one, and we will see you next time.